Hello everyone. So we'll continue our discussion of the principal stresses which we had started in our previous class. So to very quickly recall, we had spent some time discussing in detail the importance of these three coefficients, the I1, the I2 and the I3, which appear in this equation, which basically comes from if you go back to the previous slide, from this determinant. Now again to recap, the sigma that we see here, the same sigma. So this is since this is an algebraic equation of degree 3, we will in general end up with three distinct roots. It can happen that maybe two of those roots are maybe one root or two roots are equal to each other. So we'll look at those special cases as part of the problem sheet, but let's say that we have these three distinct roots, and each of those roots, the different values of sigma, they will be the principal stresses. Okay, now correspondingly, each sigma will give rise to a set of n1, n2 and n3. So suppose we obtain as solutions sigma 1, sigma 2 and sigma 3, then corresponding to sigma 1 we'll have n1, n2 and n3, one set of n1, n2, n3. Then for sigma 2 we'll have another set of n1, n2, n3, and for sigma 3 we'll have another set of n1, n2 and n3. So just like in any eigenvalue problem. Now each of those three sets of n1, n2 and n3 corresponding to each of the three different values of sigma 1, sigma 2 and sigma 3 will be referred to as the principal directions. In the language of the eigenvalue problem, you recognize that therefore the principal directions are nothing but the eigenvectors of this problem. We have also discussed that these are invariant values, okay, because we understand from the physical situation that the principal stresses at a particular point is a physical truth, and it should not depend on the mathematical representation. Okay, so no matter what the individual values of the different stress components at that particular point may be, given by different values of this sigma 1, 1, sigma 2, 2 and sigma 3, 3, the special combination in which they appear in each of these expressions for I1, I2 and I3 must be a very special combination, and so they must be invariants. Okay, so we write this here that I1, I2 and I3 are specifically they are referred to as the stress invariants. This is very, very important. They are referred to as the stress invariants. Okay, so going forward, what we'll do is we'll discuss a couple of very important facts associated with this eigenvalue problem. I believe you have already learned this back in your first year mathematics, but still it will be useful to recap two of those facts as part of this eigenvalue problem as applied to this stress chapter. Okay, so I'm trying something new in today's lecture. So whenever I have to put in some text, try to type it in. Let's see how that works. Anyway, so as I mentioned, we would be talking about two important facts associated with the principal stresses, and as they appear in the eigenvalue problem. So the first fact is so fact 1 is that the if we have a matrix which has as its elements real values, and the overall matrix happens to be symmetric, then the eigenvalues of that matrix must be real. It's a very important fact. So the eigenvalues of a real symmetric matrix must be real. And this has direct application in our study of stress, because we know that since the stress components are real, and the stress matrix is symmetric, therefore the principal stresses which are nothing but the eigenvalues of the stress matrix, therefore the principal stresses must be real. Okay, so the conclusion seems almost like a foregone conclusion. Of course, the principal stresses must have real values, but you understand that this is very much consistent with the eigenvalue problem as far as the mathematics go. The next fact, fact 2, is that suppose, so again speaking generally in terms of an eigenvalue problem, so in an eigenvalue problem, if we have the eigenvalues to be distinct, so suppose they are all having different values, then it follows that the eigenvectors must be perpendicular to each other, or in more sophisticated language, they must be orthogonal to each other. So the eigenvectors corresponding to distinct eigenvalues must be perpendicular to each other. Okay, so what it basically means is that so if the values of the principal stresses are distinct, then the principal directions are perpendicular to each other. That is what it means for the current context. Okay, so these are the two important facts. Now, what is the use of these two facts? Well, the use is that you notice that if the principal directions are indeed perpendicular to each other, then the situation is not quite different from, is not at all different from what you have in the case of your general coordinate axis, because coordinate axes are also perpendicular to each other, and here we are having this situation where the principal directions are perpendicular to each other. So this motivates us to think of it in this way. Suppose we choose our coordinate axis to be oriented along these mutually perpendicular principal directions, then what will happen? Now this might seem like a very artificially concocted type of question, like just because they are perpendicular to each other, like what is the motivation for this? And you'll see in a moment what is the motivation. Like things become really nice and clean if we do that. So what will so this naturally leads us to the next topic of discussion, which is the state of stress referred to principal directions. Okay, so so if we do that, what is going to happen to the state of stress. So when I say the state of stress, I basically mean that what will be the values of the stress components when we are sitting at a particular point. We have already seen that if you sit at a particular point, you orient your plane along any arbitrary direction, you will end up with these various components like sigma 11, sigma 12, sigma 13, etc., etc. What will happen to those components if we refer to a situation where the coordinate axes are oriented along the principal directions? So that's what we are going to write down here, that here we orient our coordinate axis along the principal directions. Okay. So you think for a moment what we are doing here. We know that if we go back to this slide, we have already mentioned that the principal plane, okay, this is referred to as the principal plane when the situation is such that the traction vector is parallel to the n hat. Okay, so basically the plane on which the principal stresses are lying. So if we are indeed orienting our coordinate axis along those principal directions, it basically means that two of these coordinate axes would be lying along the plane and one of these coordinate axes would be lying along the direction of the unit outward normal, which also happens for this very special plane to be along the principal direction. Now if that is so, then what do you think will happen to the stress components? You understand that these stress components are nothing but various components of this traction vector. So first of all, tell me about, so you think about the Tn component. Well, on the plane where you actually have the existence of such principal stresses, is it not true that this T superscript n is nothing but one of the values of this problem, is one of the answers to this problem or one of the roots of this problem? So it is actually, so if we had said earlier that it would be the roots would be sigma 1, sigma 2, sigma 3, and if we are actually considering a plane which is having a situation that the T vector is parallel to this thing, then the Tn is indeed one of those roots, sigma 1, sigma 2, sigma 3. But what about the shear stresses? So if the T vector is parallel to the n hat, then there will be simply no component along this plane. Okay, so we can quickly draw this diagram instead of just discussing it like this, that suppose we have this plane and we have our unit outward normal like this, and the plane is such that the traction vector is also like this. Okay, so what we say is that this can only happen when this is a principal plane. It must also be true that this, maybe I can draw over this just to make it clear. So this n hat, this will be a principal direction. Okay, this t vector. Okay, so this is the t vector, and you also understand that along this you have the entire magnitude to be equal to Tn, and since the unit vector along this is n hat, it is just like this. Okay, and we have already noted that this is nothing but the principal stress itself. Okay, and you understand that along this plane the Ts value will be equal to 0, so we can actually write this down. So whether it is Ts or Tt, Ts equal to Tt is going to be 0 here. Okay, this is very, very important. So you will not have any shear components. Now you understand that now what we are doing is we are orienting our coordinate axis like this. So our coordinate axis, you understand that it is like this. So maybe our x1 is along like this, and so maybe x2 is like this, x3 is like this. There is no restriction on us to say that the x1 has to be like this. It could very well be the case that x2 is along this parallel to this n hat. Now you understand that this x2 x3 plane, okay, the plane containing this x2 x3 axis, it is parallel to this plane. Okay, so we can write it down here that note the x2 x3 plane, the way that we have drawn here, the plane here will be parallel to the principal plane. Okay, which is this plane. Okay, we can actually write this here. Principal plane is parallel to the x2 x3 for this particular way that we have set it up. Had we instead chosen the x1 and x2 to be here and the x3 to be here, then of course the principal plane would have been parallel to the x1 x2. Okay, now with this understanding, what can we say about the stress components? So suppose, okay, so if we go back quickly and look at it, suppose the roots of this equation are sigma 1, sigma 2 and sigma 3. Okay, so sometimes this is referred to as the characteristic equation. So sigma cube minus I1 sigma square plus I2 sigma minus I3 is equal to 0. Suppose the roots are sigma 1 superscript, sigma 2 superscript and sigma 3. Okay, suppose these are the roots, and as we have said that these need to be distinct. Okay, these three roots need to be distinct in order that the principal directions are perpendicular to each other, going by this fact 2 which you have written down here, that if the values of the principal stresses are distinct, then the principal directions are perpendicular to each other. So we are working under that assumption. Okay, so if sigma 1, sigma 2 and sigma 3 are distinct, then we have this situation, and then this Tn value, this generic sigma that we have noted down here, it will be either one of these three, sigma 1, sigma 2 and sigma 3. This sigma will be any one of these three values. Okay, then how the stress tensor is going to look like. So you can see here that what will be the value. So since our x1 is like this, okay, since our x1 is like this, what will be the value of the sigma 1 1? So sigma 1 1 is basically the traction component on the plane which is perpendicular to the x1 plane. So what is that plane? It is nothing but this parallel to this principal plane itself. This principal plane is perpendicular to the x1 axis, so we have our plane right. So the sigma 1 1 is the stress component on a plane which is perpendicular to the x1 axis, and it is the traction component along the x1 direction. So it is nothing but this component itself, which is nothing but this Tn component itself, which is also this sigma. So what we can say is that this sigma is going to be one of these roots. Okay, let's say that it is the sigma 1. Okay, it is very much possible that it could be, I mean, in terms of values it could be any one of these, but we are just keeping things neat and clean here for the purpose of organization. So what about the sigma 2 2? So just like we have taken the principal direction like this, so another principal direction would be perpendicular to this, and we are going to orient another coordinate axis, maybe the x2 axis, along that direction. So and if we do that, then it is what we are going to end up with is a principal plane which is such that it is perpendicular to the x2 axis. So the sigma and the traction component which is along the x2 direction, that will be sigma 2 2. So the sigma 2 2 here we can say it is equal to sigma 2. And similar is the case for the third direction and the third plane. So we are good here. Now what about the other two components, the sigma 1 2 component and the sigma 1 3 component? Now the sigma 1 2 component, you understand, is coming back to this plane, the traction component which is lying on a plane which is perpendicular to the x1 axis but which is oriented along the direction x2. But on this plane we have already noted that there will be no traction component along this plane. That value is equal to 0. So the sigma 1 2 is equal to 0. Similarly, if you consider a shear component of the stress along the direction 3, so that is basically the sigma 1 3, that is also going to be 0. Similar is the case for sigma 2 1. So the element setting here, strictly speaking, is sigma 2 1. We understand that must be equal to 0, but you can also try to think of it in a very clear-headed fashion by noting that other plane that would have been present here, oriented perpendicular to the x2 axis, and on that plane also there would have been no component of the traction along that plane itself, which means that the sigma 2 1 has to be necessarily 0 also. Similarly is the case here for sigma 2 3, and we can immediately write down the other things here also. So this is the state of stress. Okay, so this is when we say that the state of stress referred to principal directions, this is basically what we mean. This is an extremely important concept, especially because if you are free to choose your coordinate axis, and you happen to choose it like this, where you orient the coordinate axis along the principal directions, then you see how nicely this has shaped up. Okay, only the diagonal elements are present, and the off diagonal elements are all 0. Okay, so this is a rather short topic, but an extremely important one as far as your understanding of the whole principal stresses concept is concerned. All right, we'll continue with our discussion of stresses in the next part of the lecture. Thank you very much.